Hi, this is Dr. Liu. In this video, I'll explain how to add vectors analytically. In the previous video, I explained how to add them graphically. So if I have a vector A, it looks like this, and vector B, it looks like this. So A plus B is, let's set that equal to R, resultant. So the R will be equal to this. All I have to do is to do the tip to tail method, right? So copy, and I'll paste that right here, and then I'll chain A with B. Copy, paste. Okay, so A's tip to B's tail. And with a ruler, I can draw from tip to tail. Let's change color. So let's just use that color instead. So this is R, right? So here's A, here's B. I exactly replicated A and B. So it's easier on the digital tablet, right? If you were to draw it on a piece of paper, you would have to use a ruler, carefully draw the length, and also use a protractor to find the angle carefully, right? So it's a hassle to reproduce results repeatedly. So let's put that all away and let's start talking about how to do this analytically. So first we want to do this. We want to take it into components. So let's make up some numbers. These numbers, let's see, we can do, this looks like something like a 3, 3. So maybe a 3, 3, x and y. And B is something like a -1 and 3. Okay, something like that. So to translate this into simple English, you start from the A's tail, you go 3 steps horizontally, and then you go 3 steps vertically. And for B, you go 1 step horizontally to the left, and then you go 3 steps up, right? So altogether, if you go A and then B, you go 3 steps to the right and 1 step to the left, then you end up going 2 steps to the right. And if you go 3 steps up and then also 3 steps up, then you end up going 6 steps up. So this tells us we can add vectors by adding their components, respective components, because 3 steps to the right and 1 step to the left they can add, but 3 steps to the right and 3 steps up they do not point in the same direction, so you cannot add these 3's, right? So here's what we do is we want to just express, oh, that's not B, let's do A vector in its xy components. So this is bx, by. So A plus B is equal to ax plus bx. So these are the x components added together for the new x component, and then ay plus by, the new y components. So 3 minus 1, and then 3 plus 3. So we have 2 and 6 as our resultant, or resultant x, resultant y. So we see that resultant x is the sum of the x of the two components, and resultant y is the sum of the y component of the A and B. All right. So this can be expanded to into more complicated calculations. So first, let's expand one. Just with one element of expansion is how to multiply a vector by a scalar. I think we have done just a little bit of that in the previous video. Have a negative of a vector, right? So we have some space here. We'll review that. So if this is a See that I was trying to do this. Copy. So this is A, and maybe I'll paste another one. So here's another one. Except that I'm going to erase. Oops, that's too much. Just erase that arrow. So if I just reverse the arrow, let's do a little more center. Okay, so if I reverse the arrow, A becomes negative A. You can also understand this as multiplying a vector by a scalar of -1. So -1 times vector A, right? So this is just -1A. So negative A, right? -1A. So this tells us if you multiply a vector by a scalar, you end up scaling the vector. And now we have this idea that A is a component. The A is a sum of x and y. So essentially, you're reverting the x direction. See, this is going to the right 3 steps. Now we're going to the left 3 steps. It was going up 3 steps. Now we have going down 3 steps. So this is actually the negative of ax and the negative of ay. So this is how a scalar multiplies into a vector. So the -1 here, right, -1 and -1 multiplies into each component so that we can scale properly, evenly scale each component the same amount of scale so that the vector gets multiplied by that vector. So along this route, if I just multiply anything, say if I come over here and say s times a, s is a scalar, just a number. And what is x times a then? Well, that will be s times ax. So you scale the x component, and you also scale the y component the same way. Right, so this is s times ax. So an example would be, say, 5 times this a that we just had. Okay, so that is 5 times the x component and 5 times the y component. So we have a 15 and 15. And maybe a 2 times b is 2 times a -1 and 2 times a 3. So we have a -2 and a 6. Okay, so that's how you scale a vector or multiply a vector by a scalar. And we can add these together, the multiplication, scalar with vector, and also addition, vector with vector, right? So I can come up with some more complicated examples. So let's take a look. I have the simulator here. So let's go to this one here. We have, let's remove some of these abstractions. So we have definitions. A is 3 and 5. So x component is 3, y component 5. And b is 2, 1. So x is 2, b is 1, y is 1. So what we want to calculate is 3a plus a 4b. So we can take a look at the result. So this is our 3 plus 4b. So what exactly is this? Let's click and select. Okay, so it has 17x and 19y. So where does that come from? Well, that comes from the component of 3a and component of 4b, right? 3a's x component and 4b's y x component will result in the c's x component. So let's calculate this on paper, quote unquote paper. So 3, 5, and 2, 1. So we have some lowercase variables that's just as good as the uppercase variables. B is 2, 1. Okay, so then we're looking for 3a plus 4b. So we're asking what is this resultant is 3a plus 4b equals what? Okay, so just like I had before, the resultant x is these two vectors x components, resultant y is 2y component. So Rx should be 3a's. This whole thing's x component, so it's just 3 times the a's component, x component, and 4 times b's x component. So this was just a 1a and 1b because I was doing 1a plus 1b, right? So 1a plus 1b. And this is 3a plus 4b. So you take 3 of your x component and take 4 of your bx component and add them together. So that's 3 times the x component is 3 plus 4 times the x component is a 2. So it's 9 plus 8 is 17. I think I remember that. And then our y is 3ay plus 4by. Don't know why I drew it so long. Okay, so the y is 5 for the a, and it's 1 for the b. 4 times a 1. So it's 15 plus 4. It is equal to 19. Okay. And r is thus 17x and 19y. And I may even ask the question, what is r's magnitude? What's our angle with x-axis? We have these formulas we had before. I'll recast them into the r. So r magnitude is rx plus ry, right? You can square them all. This is the Pythagorean theorem, and then you can take the square root. Take my ruler. Okay. So that is the magnitude is x component squared plus y component squared. So 17 squared plus 19 squared. Well, I wish I memorized these squares, but I don't. So I'm just going to use Python. And I'll just leave a space here. I'll keep writing until I need Python. And then the angle r makes with the x-axis. This is the arctangent, right? Arctangent y component versus x component, so ry versus rx, this fraction. And do I add a 180 degrees? The answer is no, because the x component is greater than 0. Only x component less than 0 requires that adding 180 degrees. So tangent minus 1, y component is 19, x component is 17. Now I need Python. Okay, let's bring Python. First I need the 17 squared plus 19 squared square root. So let's do that. Bring my keyboard over because I need parentheses. So 17 squared plus 19 squared raised power 2.5. So that's that. That is 25.5 if I wish to keep 3 sig figs. And then I also want arctangent or inverse tangent. So the y component over the x component. Because y component is slightly longer than the x component, I expect something to be slightly more than 45 degrees, where the x and y components are exactly equal in length. So we have 48.2 degrees. So let's remember that, 48.2 and 25.5. So this is 48.2 degrees and 25.5 in length. I can recall that that simulation, and we can inspect that 25.5 angle, 25.5 magnitude, and 48.2 degrees of angle with the x-axis. I think I can even display that over here, but the angles are overlapping pretty bad. Guess they didn't have anything to tell whether things are overlapping or not. Right. So this basically demonstrates how to add vectors. If you just add the x components together and then separately add the y components. Oh, they spotted a typo here. Okay. Yep. So separately add the y components together, and if the component itself has a negative, you will just use that negative. And then if you add vectors, not just add a plus b anymore, if you just do an expression of some a plus some b, then this amount gets to scale up the H component, so that H component, which was 3, scales up 3 times, B's component 2 scales up 4 times respectively, and then you get that, right? So by doing that, we also have learned this multiplying a vector with a scalar, so the scalar scales all the vector's components equally, including this -1 scale if you want a negative component. Thank you.